Okay, everyone, let's do this question 4 from the January 2020 CSEC Physics Paper 2. Okay, so for part A, for the first part of part A, the question asks, with the aid of a label diagram, state the two laws of refraction, right? So the first law that I stated here is that the incident ray, the refracted ray, right? So the incident ray, the refracted ray, and the normal are all in the same plane, right? And so you can see that because we have this flat paper that we were able to just draw all these rays and all these lines in, right? So we shown the first law that the incident ray, the refracted ray, and the normal all lie in the same plane. So that's the first law, right? The second law has to do with what's known as Snell's law, and that law states that the ratio of sine I over sine R is a constant for a given pair of media, where I is our angle of incidence and R is the angle of refraction. So I've just kind of stated that up here, that the sine of my I divided by the sine of my R would give me a constant, and we call that constant the refractive index, right, of a particular media. So those are the two laws, and this diagram should aid that, that explanation, and so we should be good for all things part A part I, and so for 4 marks, we'd be good, okay? So we have our diagram and we have our laws explicitly stated. So moving along to part 2 of that question, the question reads, when a diver under the sea shines a beam of light towards the surface of water, the light does not pass through the water-air boundary into the air above, but it reflects into the sea. So they said that we should state the phenomenon which occurs and briefly explain why it occurs, right? And so I've written about that phenomenon here. So that phenomenon is what's known as total internal reflection, okay? So that's what we call total internal reflection. It doesn't leave the media that it's coming from. Instead, it just completely reflects back, right? And that happens whenever light rays are traveling from a more dense medium. So like water, it's going from water and it's going to a less dense medium like air, right? So that's what they were saying here. He's under the sea and he's shining a light from that water, that more dense medium, to a less dense medium. And so that's when he sees the total internal reflection. And so what really happened, if we were to break it down a little bit more, is that the refracted ray bends away from the normal significantly because you're going from a more dense medium to a less dense medium. And so when that happens, the ray is going to bend away from the normal a lot. And in so doing, it ends up being completely reflected into the medium that it was trying to leave, so that water that it was trying to leave. And this happens when our angle of incidence is greater than the critical angle, right? So let's just do a little quick sketch just for clarifying this, just to make sure that we're all seeing it, right? But that's really what's happening here. It's the phenomenon of total internal reflection. And so let me just do a quick sketch here. So say this line represents my air water boundary, right? So air is up here and then water would be down here, right? We have our diver and he's shining the light, right? So this is my incident ray. So it's incident at this point. So I'm gonna draw a normal at that point, right? So that's my normal at the point. So this would be my angle of incidence I, right? And so the diver is down here and he's the one that's shining the light. And so he's shining it from water into air, right? Once we touch this air-water interface, so this line here, this boundary, what the question says is that we don't see it, it doesn't pass through. It comes right back, right? So it comes back right back into the water. where the diver is. And so that's this direction of this arrow. And so this angle would actually be your reflected angle, your angle of reflection in this case. I'm just going to write reflect, right? To show that that's no reflection and not necessarily refraction anymore. So it's just like your reflection here, right? Your reflection angle. And of course, we know that angle of incidence is equal to angle of reflection. So that's what we would see in this case. It just comes back and we call that total internal reflection, right? So that's our phenomenon here, total internal reflection. And again, we said that this happens when you have a light ray that's leaving from a more dense medium, aka water, to a less dense medium, air, right? So this is less dense, and this water is more dense. So we're going from a more dense medium to a less dense medium. And when that happens, the ray is going to bend so much away from the normal that it ends up coming back down here in this medium that it's trying to leave, okay? So it doesn't get past this boundary at all. It just comes right back. We call that total internal reflection. And the angle here at which that occurs is known as our critical angle. So that's what we said here. Whenever the angle of incidence is greater than, so theta I, right? The angle of incidence is greater than our critical angle, then we see total internal reflection, right? If this angle wasn't greater than the critical angle, what would we see? We would just see a grazing of that ray along this boundary, right? So it would just go like that. So this is if the angle of incidence, so theta I, is equal to the critical angle, right? We wouldn't see total internal reflection. We would just see a grazing along the surface. But in this case, we do see that it doesn't pass through. It comes right back. It reflects into the sea. In this case, we have total internal reflection. And that's when theta I, so this angle, is greater than our critical angle. Okay? So just make sure that you have those concepts fresh at all times in your head, okay? So moving right along, let me just clear that and move right along, right? So what's the next part? The next part of this question, so part B is saying that another diver, right? There's another diver, and what he's doing, he's outside of the water, so he's in air, and he is shining a beam of light into the water to see some fishes as shown in this figure, right? So this diver now, he's in air, right? And the fishes are in water, right? So the light is going from a less dense medium now, and it's going now to a more dense, right? That's contrary to what was happening with the diver that was in the water and trying to shine the ray out of the water, right? We're going from less dense to more dense in this case, right? So he's shining it, and this is the angle of incidence, right? At this point. So this is our normal at the point, and this is our angle of incidence. It's between the incident ray and the normal. So this is our I in this particular case, or theta I, however you choose to write it, right? And then this is our R, right? So that's R. Or it could be theta R, but let's stick with the convention that they've given. They've given the angle as I and R. So this is our R, and this is our angle of refraction, right? Which is the angle between this normal and the refracted ray. So that's what R is right here, right? And we see that we're going from a less dense medium to a more dense medium. And so we see that the ray bends towards the normal because the light is being slowed down, right? So it bends towards the normal. And so we see this angle in here as our refracted angle, okay? So moving right along, let's go down and see what else is being asked. They're asking now that given that the index of refraction, so the refractive index of water, is 1.33, and the angle of incidence is 60 degrees, as they've shown here, calculate the angle of refraction. Okay, so remember that second law that we mentioned up top. There were two laws that we said. The second law was Snell's law, and so we have to use Snell's law to find R, which is our angle of refraction. right? And so this is just pretty much Snell's law in words. So the refractive index of air times the angle of incidence is going to be the refractive index of water times the sine of the refracted angle, right? Angle of refraction. So what we're doing essentially is just rearranging this equation up here to make sine of r the subject, and that's what we did here. And then, of course, we're going to have to take the sine of both, inverse sine of both sides to get out our r, which is the angle that we want. And so that's what I've shown, that rearrangement here. And then finally, we're going to plug in the values that we know. We know the refractive index of air is 1, so we put 1 here. We know the refractive index of water is 1.33. They just told us that up here. And then we know that the angle of incidence is 60, so we just plug that in here, right? And when we do that and we plug all of this in our calculator, we'll come out with an angle of refraction of R being equal to 40.6 degrees. So an angle of refraction of 40.6 degrees, that's what we get from for our answer here. And remember, the key thing here is to realize that, you know, we're given refractive in the indices and we know our angle of incidence. If we want to find an angle of refraction, then we have to apply Snell's law to then come out with that unknown angle of refraction, okay? So that's what we did here, and we ended up with this value here. That's for 3 marks, and we are good to go. So let's see what's on this next page, our final question. So part C reads, right? Question C reads, an object 2 centimeters in height, so that's our object height, is placed 10 centimeters in front of a converging lens. So that's key, right? It's placed in front of a converging lens. So this is our what? Object distance, right? So then the converging lens has a focal length of 6 centimeters. So the question is asking us to calculate the image distance V, right? So in order to calculate the image distance V, we have to then use the lens formula because that's what relates the object distance and the focal length, which we already know, right? So if we use the lens formula, which is 1 over U plus 1 over V is equal to 1 over F, what we can do is just rearrange this lens formula, making the V our subject. So to do that, we end up with 1 over V. We just bring the 1 over U over here. So we have the 1 over V on a side by itself. So we end up with 1 over V is equal to 1 over F minus 1 over U. And of course, from the question, we know that the F, the focal length is 6 centimeters. And we know that U, our object distance, is 10 centimeters from here, okay? So we just plug those numbers in to our equation here. And we end up with 1 over V being 1 over 15, which means that V would just be 15 centimeters, okay? So that's what we got there. And of course, it's a positive number, so we know it's going to be a real image that we get. So that's what we got. We have here. And then now for part, so that's for 4 marks, so we're good, right? 4 marks, we just apply the lens formula and we get out our V. For 4 marks, we're good. So the part 2 now is asking us to calculate the linear magnification M. And the formula for the linear magnification M is V over U. So that's your image distance that we just calculated over your object distance, which they gave us from the beginning of the question. They gave us that to be 10, right? So we just calculated 15, they gave us 10. So we're literally gonna do V is equal to 15 divided by U, which is equal to 10. So we come up with a magnification of 1.5, right? And that's for 2 marks, a total of 15 marks. We are good and we are on our way to our next question. As usual, if you have any comments or any questions on anything that we did here, please drop that down below and I'll be sure to help you to understand it further. And I'll see you in the next video. Be sure to like and subscribe to the channel, okay?